This is lecture 6, example 1. This is actually just a standard programming example, assembly language programming example, so let's get to it. This is a classic problem. I love this problem because it combines two different notions here. Essentially, the notion of parity and also programming. So what I need to do here is find the parity of the value in register X20. Now, I'm sorry, in X10, and I'm going to return that parity in register X20. So what I'm passing to this subroutine is a value in X10. What I'm returning is X20. Now, if it has even parity, I'm going to return 0. If it has odd parity, I'm going to return 1, which is really nice. So typically speaking, we do parity in hardware, but this is an example where we're going to do it in firmware. And so the notion is this very much matches how humans will do this, where they'll look at the value, count the number of ones. If that count is odd, then it has odd parity. Otherwise, that count has even parity. And so let's do this thing. We can actually we're going to start with actually a very short program. It looks like the flowchart is longer than the program itself. So here we go. Parity, we call it parity X10. First thing I always need to do in these programs is initialize something. For this problem, I'm counting something, so it's going to be an accumulator, and then I am going to model this like a while, like a while loop. So I'll say value equals 0, and this is just some type of loop count on this thing, and I'll say no. In that case, I'm going to do a mask operation, and then I'm going to accumulate, and then I'm going to decrement some type of loop count and check it again. So if I test this loop and I'm done, the last thing I need to do is do one type of mask operation on this thing, and then I can call it done. Now I went through this pretty fast, but you'll see that it's not that big of a deal. So many ways to do this problem. The tendency is to make a counter out of it and do it 32 times. And we don't really need to do that in this thing because, we want to make it 32 times because we're going to check each bit, right? We don't really need to do that, and I'm going to show you why. Certainly you could do that, but in many cases you don't have to do this 32 times. So let's just put it in. Let's just write this thing. So this is parity X10, and I have some type of initialization code. So that code is going to be, essentially, I am going to use an accumulator in here, and that's going to be an X20 because that's going to be my return value, and I'm just going to move a 0 into that. So that's my initialization code. So the answer at this point, or the problem could be done already. I may not need to go into a loop, which is why I'm using a while loop and not something like a do-while loop. So the while loop is going to be, I'm going to keep doing this so long as X20 isn't equal to X0. Okay, so what I'm saying here is if X20 is equal to X0, then I'm going to jump down to done. And essentially that's this yes branch right here. And at that point, I might as well finish it up. What I'm going to do here is AND this thing use an AND immediate, and I'm going to mask everything except the LSB. So that's X20, X21. So this is a mask operation that masks the register X20 with everything but 1. So everything except the LSB is cleared on this thing, and that pretty much makes my output into what the problem wanted. So if there was an odd number of ones in this thing, I would have a 1. If there's an even number or 0 number of ones in this thing, x20 would be 0. Okay, at that point I can simply return. So essentially I've done this part right here. Okay, but otherwise in this program here, what I'm going to do is do another mask operation. Not a mask, but an immediate, and immediate. Let's call it x21 for lack of a better word. I'm ANDing the value in x20 with 1. So once again, that clears all the bits except the value in x20. At that point, I'm going to do my accumulate. What I'm doing is adding the value in x21, which is either 1 or 0, depending on whether that LSB was set or cleared. I'm adding that to x20, which is my accumulator, it's my running count on this thing. So next thing I need to do on this thing is get the problem set up for the next iteration, which is going to be a shift right, shift right logical immediate x10. See, I already made a mistake in this one. x10 1, and then I'm going to jump to loop, and the loop is the instruction right here. So typically, you know, when I write these things, I always get them wrong, and I'm not, you know, even recording these lectures, I'm going to get them wrong also. But then I'm going to go back and look at them. And so when I went back and looked at this one, obviously I got the wrong information in this one. So what I'm ANDing it with is right here is not x20, that's my accumulator, it's x10. So essentially I want to clear all but the LSB in x10 and not x20. Okay, so once again, this is like a typical mistake I'll make on these things. It's you know, it's pretty hard to keep track of these. It looks like some bizarre language, and I have trouble with it too. My approach is I don't really try to get it right the first time. I just try to get it right by the time I'm done. And so typically I'll write these pretty fast and then go back and look at them. And I take that approach simply because lots of times I'm not sure how to write these things, but I don't let that stop me. I just throw down code. It's easier to, in my mind, it's easier to fix code that you've written than it is to just generate some code. So I never hesitate to toss code down. And I think that's it. I think there's a solution following this, so we can look at it and see if it's anywhere close to being the same thing. Yeah, it looks like all the same stuff. I used maybe different register names in there. So this is, you can have this written solution, but also definitely back at the end of this there's another solution. I gave it different names, and that's it. Great problem. Once again, I like problems like this because it mixes parity, which is just a standard digital concept, with assembly language programming.